Okay. So you can hear me all right? I don't know why I have headphones on, because no one's talking to me on the other end, but okay, it's up. There we go. All right, we are continuing our adventure in streaming things to YouTube, and we'll start in just a second, so it's almost noon here in Eastern Time. And there's a lot to talk about today. So yesterday we were just getting things set up for what we're planning to do, and today we're going to get into the weeds a little bit in the course that I'm excited to share with you. So I've been posting some things to Discord. So I assume that the Discord link is in the description of this live stream if you'd like to join our Discord to interact with us. My friend Jimmy's here talking to me. So I'm posting this stuff on the data science channel. It's in there. I don't know if it's a data science channel or what. Because there's the Slack. I don't know. Subjects, whatever. Anyway, I'm putting stuff in the data science area. That's what I usually call it. So it's not going to be me the whole week. So later on, I think on Thursday and Friday, Scott Zimmerman's going to take over the stream, and he's going to talk about the stem cutting object tracker, and we've got some news about that hasn't been shared yet. So you can look forward to that from Scott. At some point, Julie Butler is going to talk about some different things. Julie from University of Mount Union. And let's see. Boop. So yeah, I'm excited to share with you those things. I'm going to give it another minute, but you may have noticed that we released a new video yesterday on air pressure, and I'm going to talk about that video for too long. So you might want to check that out when you have time. But we worked really hard on that. We probably were working on that for like 2 years, I think, that video series. So it's really nice that it's out there for people to enjoy. So I have a fan on, so if I seem like I'm blowing away, that's why. Cool. Yeah, Jimmy's at the CSTA conference in Las Vegas this week. I wanted to go. I submitted my abstract to present at CSTA. But the love I feel for CSTA isn't always the love that I receive from CSTA, and so my abstract didn't get selected. But next year, darn it, next year I'm going to go. I'm going to be at CSTA, hanging out with all the CS teachers that I can. Cool. Well, it's 12 o'clock now, so I'm going to go ahead and start. And on the schedule, the main thing that we had for today was talking about measuring air pressure with your smartphone and that sort of thing. And we are going to get to that, but because we're so early in the process and because this is like the first content part, what I want to do is I want to talk about like the big picture of this data science thing and like what I actually would do if I was in a classroom teaching this. And this course that we're doing is based on, in some ways, we did many experiments with this at Metro High School. So we did a 2-week thing in January 2023, a 2-week data science mini course, and then we did another 2-week data science mini course in 2024. And a lot of the activities that you're going to see here are were originally road tested at those experiences. So when we did that, when we went to Metro High School and we did a 2-week mini course, hour and a half a day, what did we actually do? Well, to start it off, we needed to just talk about plots and what makes for a good plot, what makes for a bad plot, and that sort of a thing. And so So we have a link for bad plots, right? We have a link for good plots. It's more fun to talk about the bad plots. So this is what we did with an actual group of students, and you can feel free to use this link. So this link is in the Discord. So these are all the bad figures that we could find, essentially, right? So we have a long list. I don't even necessarily need to go over this list, but this is just in no particular order. This is a figure that is not a great figure. Okay, so you can put this in front of students and tell them, like, there's some problems with this figure, and try to get them to tell you what the problems are. And so here we've got the x-axis is the increase or decrease in the deaths per day from COVID. A lot of the plots are from, there were so many bad plots from COVID. They're good plots, but there were many bad plots too, right? So this one has, deaths per day, whether that's getting better or worse, because like every day it used to be the state governments would say how many, or the countries would say how many COVID deaths they have that day. And then, so this is the increase, and then this is the average number of deaths per day. And so it ends up sort of looking like the cycle. The point is that, like, this is just not a helpful way to look at the COVID data. It's like, as the number of deaths are increasing, then the average number goes up, but then it decreases and it goes down. I don't know. It doesn't really tell you much. So I could do this all day. So here's a particularly straightforward one, right? So what's wrong with this plot? So if you look at this, there was 570 votes, and the question is, should we remove a car lane from this bridge and replace it with a bike lane? And, only 53 people voted yes. 570 people voted no, but if you just looked at the view graph, it seems like people were almost unanimous that you should remove that car lane and replace it with the bike lane. So this is some pretty sketchy figures here. So this is a bad figure, right? And we can go on, and we can develop, a theory for what makes for a bad figure. So here's another COVID one. So you've got this many cases of COVID on this day, and then this day, it actually went up. So it went from 3,200 to 3,800, but now the bar is down for some, like it's this inverted thing, and it went up again to 4,000. So that's not good. In general, there's not going to be any one, there's no one theory of what makes for a bad figure, right? There's no one, So there are many different ways of making a bad figure. So in this one, this is the price of gasoline in India. It went up 20%, it went up 75%, and then it went up another 13%, but according to this view graph, they're taking credit for somehow, it seems like they decreased it, and they didn't decrease it. So there's no one framework that makes a thing a bad graph. There's an infinite number of ways of making a bad graph, and that's something you can talk about with your class, but you also should talk about what makes for a good graph as well. And sometimes bad graphs are bad not because they're intentionally manipulative. Sometimes bad graphs, and forgive me, this is one of my students made this plot, and the thing about it is that it's just kind of hard to read the axes here. OBS Studio is disconnected. Right, hopefully I'm back. Okay, hopefully I'm back. So I was saying about this figure is that there's nothing really wrong with this figure, but it's got like three different color scales, and it's got all this font that's there. So there's sometimes figures turn out to be not so useful, not because you're trying to make it bad or anything like that. So I'll show you one or two good figures, and then we'll talk about more of a philosophy of what makes for a good figure and that sort of a thing. And let's see what this is. So this is thought to be a good figure. And so this is with time. It's showing how different industries have job gains while other industries have job losses. So you always have people that are losing jobs, and you always have people that are gaining jobs. So just one number isn't so useful. This has multiple numbers, so that's one example. This is just a very clear this is from my research. This is a very clear figure of what's going on in this experiment. So the font is easy to read. There's different colors to show different things, that sort of a thing. This is another one. The font's kind of small here, but there's colors, and it's trying to tell you useful things. This is an interesting data set because it's about movie data. It's about when a movie came out in the box office, how much money did it make, and then how much money did it make over time, and the area of it. I mean, you could debate whether this is a good plot or not, I think. And this is a good thing to have a debate with your class, right? So, is this a good plot or not? So, like some of the films, they had a big box office run, and then it sort of goes back down, while there's other movies sort of stick around for longer, that sort of thing. Like Ratatouille. No, yeah. Ratatouille there was big, and then it's sort of holding on, I guess. I don't know. It's an interesting data set. It's an interesting way to plot it up, because some movies are like, so one of my favorite movies is some of my favorite movies didn't do so well in the box office, but later on they became cult classics, let's say. So these are some good figures. So if we were teaching an actual data science course, if you put me in charge of an actual high school data science course, I would show some figures. We'd try to come up with some general ideas of what makes for a good figure, what makes for a bad figure. And then what we would do is we would have students like actually read this chapter from a book called Effective Data Visualization by Stephanie Evergreen. And we really like this book, and the book does a great job of talking about the philosophy of making a good chart, because there's, in principle, for the same data set, there's an infinite number of ways of representing it, right? And so this book tries to give you some ideas of, like, here's 5 different ways of making a chart from the same data, and here's why this one is, or that one is the most helpful way to do it. So we like it from that reason, because it's nice and practical. And another reason why we like it is it has a lot of Excel stuff in it. So it's designed towards Excel. So we bought it. You'll have to buy it for your class if you're going to buy it. We bought it. Maybe we're not supposed to do this, but this is the first chapter. And this is before we get into any kind of spreadsheet stuff. But the first chapter is just about like, what is the point of doing all this stuff? Like, why we visualize? What is the point of visualizing, right? And the answer is not that we visualize because there's numbers and this is just understood of what you're supposed to do with it. Instead, it's about you visualize because you're trying to tell a story with data. You have a story that you've thought about the data, you've done your homework to try to understand what it's telling you, and then the story that you've heard from the data, you want to communicate to someone else. And as a scientist myself, sometimes a lot of the work we do is trying to figure out what story the data is telling us, but then an awful lot more work goes into just trying to explain that as concisely as we can, or with figures. And I showed you some of the figures that we had there. So, so this is a great example of yeah, these are great examples of different ways. So if you have some data set, you can sort of highlight this thing because you're trying to tell this story, right? But if you saw just the raw data from that, it might not be obvious that that's there. Um, so, and yeah, sometimes visualization can be harmful, different types of plots, tell the story with data, right? So we just have the students read this. Students need to beef up their reading skills. It's okay to just give them a PDF and tell them to sit and read the darn thing. And that's exactly what we did when we had the opportunity to teach a 2-week class with students. So that's the first thing I wanted to say is that everything we're doing is part of this wider attitude of trying to tell stories with data. And so those are two great places to go look. Another great place, DataSpire, YouTube. A friend of ours is Kristen Hunter Thompson, who runs DataSpire, and she has all this great. She just started in the last year making a YouTube channel, and we really encourage people to go check out her YouTube channel. She's been posting stuff for the last couple months, and it's all about making sense of plots, which plot should you choose, pie chart versus bar chart, this sort of thing. So definitely check her out in terms of, she's been doing data science since before it was cool, so definitely listen to Kristen and what she has to offer. So that's what I wanted to say about all that. And we're listening in the chat, we're listening in the Discord, so please, anybody, if you have questions, please go ahead and jump out. I'm going to go ahead and, let's see. So if those are the first kind of things that you would do, what's the next thing you would do, and what would potentially be one of the first things you could possibly do with the class? So there's a worksheet that I made a while ago, and it still hasn't really been adapted yet for more general use, but I was teaching an astronomy course, and what I did was that I challenged the class as an assignment to try to make a model solar system. So every student or every group had to design their own model solar system, and to try to scale it to fit in a classroom or a gym or a baseball diamond or a basketball court or a football court or a soccer field. And that is a nice experiment of sort of looking at what are the real distances from the planets to the sun, and then trying to adjust that and to scale it and multiply it so you can have figure out what the positions on a meter stick would be to actually put those in, say, a basketball court, something like that. So that is one of the simplest things that I can think of that gets people pointed in the right direction. A relatively simple thing, another relatively simple thing, is this air pressure thing that we've been working on. And so we just posted this video to the YouTube channel, I think it was yesterday. Yes, I would like to visit YouTube. And our friend Jessica Culp is in these videos. And the basic idea of it is that your smartphone, pretty much all smartphones, it's rare for me to find a smartphone that can't do this, they all secretly inside of them they have pressure sensors. And so what you can do is you can go up and down a stairwell. And so if you go to our YouTube channel, the second video, the first video is about installing the app and how to use that. And then in this part 2 video, Jessica goes up and down a stairwell. This happens to be the stairwell in the physics department at Ohio State. And so she goes up and down the stairwell measuring things over something like 4 stories. And she gets really nice data from it. Now, for those of you at home, if you don't have a 4-story building that you can go up, the message I have for you is that you should still be able to do this. You should if you download the app, so we like the Arduino Science Journal app, but there's other apps that work too. So especially if you go searching around for like physics apps, a lot of the physics apps are able to detect this thing. So what's amazing is that these smartphone apps are so darn sensitive. So it's giving me like 5 digits of precision on this pressure. And if I put my phone on the floor, so I'm trying to prove to you that you don't need 4 stories, right? So if I put my phone on the floor, it says 982.6265, something like that. And then if I put it above my head, it gives me 982.4. So even just changing it from my feet to my head has produced a detectable change in pressure. That's just how sensitive these things are. So you could probably do this activity just with that. In the school that we did our data science mini course in, they didn't have 4 stories or anything like that. So we managed to find a ladder, and we just climbed a ladder, and we got decent data from that. So the worksheet that she's working from looks like this. So we tried to do a good job making it look nice, and it gives you some advice on finding this app and that sort of thing. And she's just kind of working through it part by part. And in a physics class, we talk a lot about 100 in my physics class, we talk about a lot about 100 kilopascals. If you wanted to skip that part, that's okay. But so she's just kind of working through it step by step, and this is where you can put in the data. On my phone, the data comes out in hectopascals. You convert that to pascals by multiplying by 100. And then what you end up with is you find kind of a weak decrease in pressure as you go higher and higher, right? So one of the questions here is, do you expect the pressure to go up or down as you go up the stairs? And if you think about how at higher altitudes, here I'm in Ohio, but if I was in Colorado, the air pressure would be less. Well, then just that fact alone gives you a good guess that going up should make the air pressure go down, right? And so she fills out all the data for that, and then she finds the best fit. And then the best fit gives you rho g, and then if you know that gravity is 9.8, that can tell you what rho is, which is the density of the air, that sort of a thing. And at the end of the day, so you find what this slope is, and then the fun part is that you want to try to a fun thing to do is to estimate where the edge of space is, right? And so if you assume that this formula goes all the way up until the point where the pressure becomes 0, and we could talk about that assumption in a second, but if you assume that this formula goes all the way up, then you can solve for the height at which this pressure becomes 0, and that becomes your estimate for the height of the edge of space. And if you watch the video, you find that the height of the edge of space is something like 8 kilometers, which is, what is that? That's a couple miles. So that's too low. If you Google like edge of space, you will find that the edge of space is, I forget if it's 60 kilometers or 80, I think it's 80 kilometers, the Kármán line. And so the estimate ends up being about 10 times too low. But that's okay. I mean, we're just doing crude estimates here. My feeling is that there's a lot, like, I really love atmospheric science. My feeling is that this probably annoys atmospheric scientists for us to sort of stand up here and say, well, let's go ahead and assume that this goes out to the edge of space. So as a physicist, I feel like I'm going to be doing I'm going to annoy a lot of atmospheric scientists with what I'm doing here. But in a second, I'll talk about how this is, what the actual trend is here. So you end up with a height of the edge of space that is about 10 times too low. But the problem is that we assume that this density was constant all the way up from the ground, where I am at, all the way up to 8 kilometers in the atmosphere. And that was the crucial mistake. And so if you think about how the density might be decreasing, then it becomes more plausible that the edge of the atmosphere might be all the way up, closer to the 80 kilometers that it actually belongs. So we like this activity, and there is solutions to this activity that I did post to the Discord, and so we can have some example outputs that give you 100 kilopascals tends to be pretty close to sea level. In Ohio, we're somewhat close to sea level, so we come out as something like 97 or 98. If you're in Colorado or someplace high up, it's going to be less than that. But that's just standard temperature and pressure is 101 kilopascals, if you're a chemistry teacher out there watching. And so we just have some example data, and you can feel free to steal some of this data if you want to use it. Yep. So there's some examples. You can look at it from the video. You can get it from here as well. So we provided that for you. Now, I promised that I would talk about extensions to this activity, and there is some things that that can be extended to it. So the pressure sensor, it's not like none of the data that we have, like the data here is not an error. So there's no problems with the data that is being collected from this stairwell. The problem is that we just didn't go high enough, right? So if we could have gone high enough, we would have reached the point where it really matters. If we've gotten high enough, then instead of the pressure dropping off linearly, and in general, the reason that I love this activity so much is that the data is very linear. So if you plot it all up, like so, like as a teacher, you're always looking for linear data, and here it is. Oh my, look at that! Like there's so much linear data in like middle school and early high school stuff, and like here's a great example of a linear data set, right? That students can collect with their phone. So there isn't any problems with this data. It's just that if we had gone out further, like way out, there, what happens is that eventually this data sort of starts to flatten out, right? It starts to go from a line to more of an exponential. And that's the thing that we're not capturing by assuming that the equation goes like this. So there is a, see if I can find the site. No, there we go. So this site exists. I'm not claiming that this is an easy to use site, but I put the link on the site on the Discord. So this site has at different stations in the United States and abroad. There's different weather stations, and those weather stations take measurements, and then the data from those measurements are saved here. And so if you click here, you can find all of the data, and you can download a zip file for them. Now, my understanding is that the one that starts with US are US based, and at one point I was able to figure out that, and I don't quite remember how I had figured this out, but at one point I was able to determine that USM 72426 is actually within Ohio. And so I was able to go to there, and I was able to download that file, and I was able to look at it. Now, the thing I love about this site is that it does have balloon data. So like the data in these files do include balloon data, in which they have a pressure sensor that goes up quite high into the atmosphere, and you can see, let me show you that pressure, and you can see that if you do that, then you can see that the trend is linear if you're close to the ground, right? But as you go higher up, it starts to look much more exponential. And if you've taken physics training or chemistry training, you might know the factoid that if you have a gas that, you know, is in a place that has gravity, and the gas is the constant temperature, then you should naturally get a perfect exponential, by the way. Our atmosphere is a little bit complicated, so it's not perfectly exponential. And this is one of those things where the atmospheric scientists would get annoyed at me that I would even imply that it should be perfectly exponential. But as you can see, it's fairly close to an exponential, right? And I think this is a fascinating thing too, because if you look at advanced high school math, where you're getting into exponential functions, you're trying to figure out what in nature actually gives me an exponential function. I'm tired of financial data sets, right? So this is actually a pretty good example of an exponential function. And so a thing you can do is you can plot this up in a spreadsheet program. And if you wanted to take another step, you could actually plot it logarithmically. So if I was in charge of a data science course, a thing I would want to do is plot it up, is make sure students know how to plot things logarithmically. And so you can configure this axis to plot the log. And then here, just for example, I compared it to a purely exponential model, and you can see that it's not perfect, but it lines up pretty well. So if you plot things, if there's an exponential relationship, and you plot one of the axes like this, then it should give you a line if indeed it really is an exponential relationship, and you find that indeed that it is pretty darn close to it. So this is a thing you could do. I think we're still, maybe in a few months we'll be able to release another activity that's in detail about this. If you wanted to do it for yourself, you would have to download this data. It's a bit tricky to do it yourself, but if you want to do it yourself, you have to download this data and unzip it, which isn't too hard to do. And then you get this sort of data here, which is not so easy to read. But if you look closely, this third column is actually the pressure in pascals, which is great because that's what we've been thinking of it as. You'd think they would give us some other pressure unit, but no, it's in pascals. That's good. And then I believe this is the altitude. So the altitude goes, as the altitude goes up and up and up and up, you can see that the pressure goes down and down and down and down and down. And so it gives you all this nice data. Now the raw data, what's annoying about it is that it has like letter B here, and there's a B there, so you have to like manually like delete the B's, which is an example of data cleaning, right? Because sometimes we need to sort of look at our data and sort of manually edit it a little bit, not because we're trying to change the numbers, but we're just trying to get it into a format that's more useful. And I believe the raw data, so the idea is that the raw data looks like this. This is my advice, by the way, if you're going to do this at home. The raw data looks like this. You get all these minus 999s because it doesn't have data. So what you do is you take the raw data you can download from the website. You go all the way down to the very end of it. And at the very end of it, so like these are all minus 99, right? But it's at the very end of this file is where you can find this pressure data. And it says, what day that they did it, so you can tell that this is from 2022, probably June 17th, that sort of thing. There's other numbers. One of these numbers I think is temperature. But these are the two columns that you need, is the pressure and then the height. I believe this is the height above the ground in meters. And so you have to delete the B's and stuff like that. But I'll post the version of the file that we went ahead and deleted. So that is a way that you can do data science, spreadsheet skills, data cleaning, and Algebra 2 math function concepts. There you go. So eventually we'll do a nice video about all this, but I just wanted to point it out. And this isn't going to be the only time the exponential relationships are going to come up in the STEM coding data science curriculum, but it's the first time it showed up, and I'm happy to share it. Now, if you feel like this is too advanced, that's totally cool. It's your classroom. Like, if you feel like this is overwhelming and you just want to stick with the going up and down the stairwell, that's totally fine. I'm just here to say that there is an advanced extension of this thing where you can hit those Algebra 2 standards. Because one of the debates nationally going on right now is, like, what is data science supposed to be doing? What is high school data science supposed to look like? And there are concerns that it doesn't hit as many of the advanced math concepts, and which raises concerns that we're not preparing our students for college experiences that they might have, right? And so it's important to think about how can you connect to some of these Algebra 2 pre-calculus type concepts. For me, I love logs because I use logs all the time in my research, but don't forget that even if a student is going to go off like installing internet, cable internet, something like that, they're going to be measuring decibels. Decibels is related to the log, and so teaching them about logs is teaching them something that they will encounter at some point in their lives if they do anything technical. It's not just PhDs in physics that do logarithms. It's regular folks just trying to get stuff to work as well. It's important to know that 100 decibels is quite a bit louder than 80 decibels, right? So because of the way that logs work, and so you can begin to introduce them to that, and then related to all that, all the things that you learn from linear regressions with the linear data, you can also learn if you take the logarithm first, and then take the try to get the slope of this thing in log space. That's another thing you can do as an extension. So that's what I had to share for today, and so I'm happy to look at the chats. I'm going to stay on for another 5 or 10 minutes, seeing if there's any questions. Tomorrow I'm excited because I believe we're going to talk about solar cell data, and so Julie Butler and I have been working. So some of the solar cell data is actually from my actual house, and solar cell data is a great data set because it's messy. And students have to use different commands to sort of sum the data and average the data, that sort of a thing. And it changes from year to year, but there's also these trends because it turns out the solar panels actually degrade over time. So when you install solar panels in 1 year, 4 or 5 years later, they might not be working as efficiently as they were when they first did. And you might want to think about, when should I replace it? So I'm really excited to talk about the solar cell data, which has never appeared on the YouTube channel before. And so that's what we're going to be talking about tomorrow. So I hope that you tune in to check that out. And I'm going to, in a second here, I'm going to see if there's any comments here. But thanks for attending the live stream for today. Cool. All right, let me see what's going on in Discord. See if there's anything I should check out. All right. All right. Okay. All right, I'm getting thumbs up from Julie and Scott on my phone here. So thanks, everybody. We'll see you again tomorrow at noon Eastern time. And feel free to check out the Discord for many of the links that I posted today to learn more about it. All right, thanks.